to the class. I see some of you have, taken this class last year. Basically, I will repeat the same thing. So I hope you catch up with this idea. So this is a part of real-world data circulation program. And also, this is also open class for Graduate School of Engineering and Graduate School of Informatics. So welcome all to this class. Real-world data circulation is the PhD program. And we are very happy to, having the student from 4 different graduate schools. Those are engineering and informatics, and medical, and also economy. So the real-world data analysis, that is the name of this course of lectures, should be somehow, fundamental and also not so highly technological, but I like it be one of introductory ideas which would be given to you. How or what should be, very important for applying the recent data science technologies to real-world analysis or real-world problems. So my part is dealing with time sequential data, which is, in other words, known as signal. Okay, image or video is signal, and also speech, audio, those are also signal. And accelerometer output, those sensing data are also known as signal. And because of its association with the sequence or time, it is very important to understand the periodicity of the signal or data, and also, prediction or, regression is another very important feature. But anyway, what I will introduce is the very, very first phase of dealing with the time sequence data, which is denoising. How can we eliminate the noisy component from the measured data? You cannot be free from noise when you deal with the real-world data. If you are thinking about theoretical data, it is fine. But once you measure something, you cannot be free from noise. And there are a huge amount of technologies to eliminate noise. But I hope you understand the very, very fundamental level of knowledge of how to deal with noise. Those are, roughly consists of 2 situations. One is the noise is deterministic, like contaminations of 2 different speakers' speech, or like I will introduce power spectral noise, which is contaminated from the power line of the measurement system sometimes. And the second aspect is the noise is completely random. That means that you cannot know how the noise changes in terms of the mathematical representation. So that is common case, of course. Noise is usually random. So I will very much, I will introduce a very, very fundamental idea how to deal with random noise. So that is the rough content of my 1.5 hours talk. Okay. So what is signal and what is noise? And also, how do we reduce the noise which is contaminated to the target signal? In 2 cases, deterministic noise and also random noise. Okay, and before I'm talking about that, I'd like to briefly introduce what is data and what is signal in terms of the real world, real world knowledge. So this is the table which tabulate the population of Nagoya words. My pronunciation sometimes is very bad, but there are several words like Chikusaku, Higashiku, Kitaku in Nagoya City, and each of them has their own population. Okay, so this is a table, and when you depict these numbers into this kind of figure, then this is something informative for you. But usually we call this kind of figure as a bar chart, maybe. How do you call it? Bar chart, maybe. Yeah, so bar chart, and you see several, kind of figure, or how do I say, envelope on that chart. But probably you learn this very fundamental difference between bar chart and line graph. When you connect this point with the next point, you're gonna get a one broken line, set of lines, which looks very consecutive or continuing. But those continuum doesn't have any idea, because Chikusaku and Higashiku, the order of this name of the words are not so much meaningful, right? There's no order. But when you depict the different horizon, like for instance the year and the month. So monthly total population of Nagoya City looks like this. And when you connect each individual observation or survey result, will give you a very continuous line like this. And the shape of this line has meaning. For instance, this is glowing. So Nagoya City population is growing. And also it has kind of a dip for every year, March, April, because of the social movement of the population. In Japan, people move at the end of the physical as well as academic year, like March or April, right? So this dip in this figure shows another different aspect of the data. But anyway, connecting these points and organizing one line is meaningful. And we understand that this is signal because this is the ordered data, and its order has also meaning. In this case, time horizon. Okay. And if you take this horizon into a place, location, you have another, how do I say, representation of the data. Usually it corresponds to the image, because image has a 2D, two-dimensional horizon in a length or displacement domain. So it's very important to understand the difference between simple bunch of data and sequence of data, which are signal. So in this lecture, I will use the word signal for representing these sequence of data in order. Okay. Again, when you understand my idea to discriminate the two different things, one is simple data and the other is a signal, then you can somehow, imagine the mathematical representation of data. Okay. Usually we use this kind of representation in engineering field or computer engineering field. So X, this is the name of the variable, and place like this, and you put independent another variable small n, which usually is the integer or natural value, which means that discrete in a computer sense. But in the real world, it is usually continuum like T. In that case, we usually use the round branches like this, xt. And it's much more look like a function. So x is the name of the function, and t is an independent variable. But this is in a computer era is more familiar mathematical representation. And important thing is like this. N is discrete number, therefore this is not a continuum, but this is the sequenced data. And usually we have the length of the signal, which in this case is large N, which starts from 0 to large N minus 1, or from 1 to large N. That doesn't matter. But the length is large N. And this representation is a very fundamental representation of the ordered sequence of data. In other words, signal. So this is quite fundamental idea. Okay. And by means of this mathematical representation, we can calculate some properties which is behind the signal, observed signal, based on the very fundamental calculation like adding or substituting or things like that. In this case, this is a zooming up part or line of the signal which I showed in the previous slide. Nagoya city's population. And as I mentioned, we can know that there are periodical component like this for every year. Okay, so periodicity is very important. Another idea of the signal, but I don't go in detail about that for this moment. I will describe it later. But anyway, periodicity is superimposed on a gradual trend of increasement of the population. And if you look at this particular 5-year period, the average number of the population is like this. So you can calculate by mathematics the very fundamental, characteristics of this data. Those are average, and also a trend, and also the periodical component. How do you calculate that? How do you calculate the average of this 5-year population? How do you calculate? Mm-hmm. By log? Log.
That means C is equal to 1 by 10.
Uh-huh. Okay. So simply summing up all data and subdivide it.
Average.
Okay, average. Okay, it's average. And how do you calculate trend? How about you?
I think is like observe the direction.
Yeah.
And see the change.
Yeah. So how do you calculate the trend? That kind of property by means of math.
Like imagine it as a straight line and think about.
Yeah. Fundamental idea is that this is, supposing that this is straight line. Then we can, calculate the tilt of this straight line, and that can be, understood as a trend. So you naturally proposed our model, right? So Nagoya city population is monotonically increasing, proportional to the time. So that is very important. That is, really, heart of the data analytics. So how about periodical component? Do anyone can propose how do we calculate periodical component or model the periodical component from this figure? How about you?
I'm not quite sure.
You're not quite sure? Okay. Okay. If you are engineer, then you can somehow propose a model. But to me, this is a natural, quite natural way of calculation. For instance, the averaging. It's very easy to sum up all those data and divided them by the total number of the sample. Okay, this is a very simple averaging. And trend. Yeah, you are very smart to build a model. But even without building a model, we can somehow calculate this line based on the local average. Like for instance, this is a 12 month. Therefore, each 12 month, you can calculate the average, blah, 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 blah. That can cancel out this periodical change if you take the 12 months or more, right? Because in that time span, you see the peak and negative peak in the period. Therefore, blah, blah, blah. So that is just calculation of, again, local average, but indexed by the time index m. So you pick m and calculate average, 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 average. Then you're going to get another time sequence, which can be regarded as a trend without supposing any model. And when you calculate the average and trend, then you can subtract these two components from the original data. That's going to give you the residual part of the data. That's going to be very, very relevant to this periodical component. So you don't need any difficult or any complicated math. You just calculate averaging, sum and divide. That's enough for calculate or understand this population change. In other words, you can estimate the average, trend, and periodicity. Okay, so this is known as descriptive statistics. Okay, you better to understand. You better to know the word descriptive statistics. Descriptive statistics is a simple idea without any sort of model to describe the data which is obtained through real-world observation, or in other words, stochastic data. But this is nothing more than very simple math. What we know currently is fit a model like you proposed, which is known as machine learning or estimation or statistics based on the estimate. Okay, then what that will be is very important. But anyway, before seeing that kind of things, let me show you the calculation result of the local average and also the global average and the result of the subtraction. So you can easily see that what is a periodical component and how large the population changes every year, and how gradually the population is growing, and also what is the rough population of Nagoya city. These are knowledge can be easily extracted from the signal. Okay, So another idea is the mathematical model and fit the mathematical model to the data. That is fundamental idea of the machine learning, data analytics. Okay. Okay, that is like this. We have already know or assumed that the trend component can be represented by simple line. Okay, you propose that. This is very reasonable. I agree with you. The very fundamental change of the population can be understood as a monotonical increasement. And the tilt of this line can be represented by a single number, A1 here. And if you calculate the product of A1 and N, then we can plot this line. And of course, A0 is the average value, like this. Then, and how or what will be the mathematical model of periodical component will be? Okay. This can be, somehow, do I say, people dependent. If I were you, or if I am facing this problem, I will use this function, cosine square. As you know, that sinusoidal, signal is shaped like this, plus and minus, plus and minus. But I see this is a single polarity, which means that the plus part of the sinusoidal signal are aligned with respect to the line time. So I will put this model for understanding the signal, but it's up to you. You can use a lot of different variations of models for doing that. But to me, this is very simple. So periodical signal. And most important thing here is that when we suppose or assume a model like this, there are several unknown parameters. In this case, A0, which must be corresponds to average, A1, the trend term, and A2, periodical term, and most importantly, phi 0, phi O. This is the periodicity of this sinusoidal signal, and phi is a phase. Okay, and if you are genius or very, very lucky, you may completely describe the observed PM, that is the population at that moment, using this simple mathematics. But it is never the case, okay? Always natural data, real data cannot be like this. We have a error term. So error term is very important. If this term is much, if this term is closer to the Gaussian distribution, then the model is better. You should understand that. When this is closer to the Gaussian or standard distribution, that means that this model is quite correct. But anyway, our problem becomes then the estimation of these 1, 2, 3, 4, 5 unknown parameters, so that the residual error power becomes least. So that is another aspect of the mathematical influence based on the signal. Previous time, in the previous step, we simply calculated the ad hoc value like a local average and also a global average or subtraction, things like that. But in this case, this becomes more analytic problem. You solve some sort of equation or inequality under the assumption that the most, or least error power is the best, estimation of A0, A1, and A2. Okay. So again, this problem can be formalized like the model parameter is A0, A1, A2, and phi or omega 0. This is assumed periodicity, I mean. And the error is like this. So estimate, or how do you know, or how do you get to know the omega 0? This is an interesting question. Come. Of course you can observe this data and roughly estimate this, or probably you can optimize omega 0 based on the mathematics. But it becomes obviously highly nonlinear problem because these terms are very simply put it in this equation, but this is in a highly in the argument of the highly nonlinear function. Therefore, you cannot easily derive the best value of omega 0 in general. But on the other hand, we know that because this is the population change, therefore, the 1 year is a quite reasonable guess of the social aspect of the population change. Therefore, this can be a 1 year term, and you can convert the 1 year period, which is 12 samples, into the angular frequency by this equation. Then you can use this value as a super parameter or hyperparameter. And then you can then calculate these values as a very based on the very simple procedures that I will describe later. And then once you get this equation or function, then that becomes a very nice description of the Nagoya city population, and you can use this equation for predicting the future population or extracting the sudden change from this trend. Okay, so like this, we can decompose the real world data into several pieces of the signals. And each individual signal has its own mean. So the noise reduction problem can also be regarded as the decomposition problem because we usually observe one variable and that observation contains the real value and noise value. And we need to decompose real component and noisy component. That is typically described by this. Xn, this is observed signal or value. Small s, and this is the real value. And d, displacement or is the noisy value, okay? So all you can see from observation of the real world is only this. But we can never be free from this, real value and noise value, okay? So when we can decompose, like previous cases, the signal into two components, like a trend and periodicity, we can somehow, eliminate this part based on the equation. But reality is not so simple. But anyway, mathematically eliminating the additive noise. By the way, these noise formulated by adding is sometimes called additive noise. On the contrast we may use the word convolutive noise. Convolutive noise. I didn't put this word, but that idea is quite important. Convolutive noise or productive noise, which means that Sn is convolved with the noisy channel. In other words, Xn is the, for instance, A times Xn, Sn. So real value plus B times Sn minus 1. So you may notice the difference between my voice and I try to speak in the same way, but the room reverberation gives you a completely different sound to your ear. Because when I facing at this whiteboard and saying the main power of the sound signal reaching to you is after first reflection based on whiteboard, which is echo, and echo can be represented by the summation of the previous sample into the current sample. Okay, echo. And this kind of noise is sometimes referred as the convolutive noise. And this is much more difficult. Convolutive noise. Well, someone say productive noise, but I don't like that word. Convolutive noise. Okay. But anyway, this is an additive noise, and additive noise is much easier to deal with based on the several things, and also much common. And mathematically, this equation gives you the idea that the real value can be easily calculated from subtracting this value from this value. You know, elementary school student can say that, oh, this value can be calculated from this minus this. That's correct. The issue is that we don't know the exact value of this. Okay, that's why I say this is the deconvolution separation problem. Okay, so the issue, of course, is how we don't know. But once we know these values, then it is quite easy to eliminate the noise from the noisy signal and get a clean signal from the real world data. Okay. So again, and the issue is how do we know the actual noise signal out from this? Which is actually asking, what is noise? Or what do you like to know from this? Probably there's no real value in this case. Observation is only real value. But what if you like to know the trend of this population, then periodical fluctuation must be noise to you. If you like to know the periodical increasing and decreasing of the population, then trend becomes noise. Okay, so noise is, it depends on your purpose of signal analysis. And one typical noise, if you are engineering field, is PSN, power supply noise. Okay. Do you guys have any experience measuring the very naive phenomenon based on the electrical measuring. Nakagaito-san? What does this mean? If you studied electrical engineering, actually I studied electrical engineering undergrad. Every 3 days a week, we spent half day experiment and measuring a lot of things, like a huge voltage electric system, and also a very tiny circuit of the primitive semiconducting system. Yeah. I'm in the same class with Amano sensei, and I don't remember that I shared the same experiment group with him, but all those guys are doing a lot of experiment. And one of the headache always to us when we measure the very tiny system is the power supply noise. When you connect your system to the power supply, then it produces these kind of things. 60 hertz fluctuation or noise contaminate with the very sensitive small amplitude signal. So this was a headache of us, and at that moment we do not have very good computational system for the use of the measurement. We use how do we say 計算尺? Not an electric calculator, but a bamboo calculator, not a soroban. How do you call calculation scale? Does that correct English? Calculation scale, okay. So we use such kind of device for calculating or plotting these kind of things. So anyway, that was a very interesting challenge to us. But 60 hertz signal always comes to us and makes a final result of experiments or labs misery. But nowadays, we can use the computing system, which is a personal computer, or any sort of mobile devices can sample this data and eliminate this component easily. Because we know what is the power supply noise. Power supply noise in our area is a signal which has the 60 hertz periodicity and very, how do I say, clean 60 hertz or pure tone, I mean. Do you understand? If you guys studied about spectral analysis, then you may know the idea of how the signal is simply or much more simpler tone or sinusoidal signal, which means that that signal contains only fundamental frequency component, not a higher order frequency component. And the power supply noise is quite clear and consists of the fundamental frequency component. In other words, it looks like this. Don't blame me in the bad plotting, but like this. So the periodical and things, and also because this is 60 hertz. So do you know these kind of things? This when you plot against to t, then if this signal is 60 hertz, in periodicity, then this becomes the 60/1 second. And in other words, the angular frequency of the signal is somehow 2 pi over 60 when you sample them by the by the time like 1000. Okay, but so it's a very simple signal. Therefore, we can we can subtract. We can somehow simply subtract the very pure sinusoidal signal like this, which is the 60 Hz sinusoidal signal. When you sample this data at 1000 Hz sampling frequency, and then you can estimate the real value. Okay. So based on model, you can eliminate this component. Do you agree? Okay. Probably you don't clearly understand what I like to ask. We know that the power supply noise can be represented by this formula because of its nature. And as I said, once we get the measurement and also noise signal, then it is easy to estimate the real value by subtracting the noisy component from the real observed value. It sounds very, correct, okay? Yeah, but in reality, it's very, very difficult because all we know is periodicity. We don't know the amplitude, and more importantly, we don't know the phase. So shifting this sinusoidal signal like this makes you misery. Sometimes it gives you more noise. Okay? And deciding this and this is another problem. And currently, because you can use the computer system, we can somehow identify the better or best A and phi based on the data, because we can calculate the error of this value. But when I was a student, we could not do that, at least in our lab. So this doesn't work, actually. This doesn't work in general. All we need to do is to estimate the accurate amplitude and accurate phase. And that is very much difficult, probably more than you think. So this is an example. You see, there are two sinusoidal signals, cosine 6 pi over 50n. And if you subtract the same signal from the original signal, of course, the output is 0, regardless of the time, because we do subtract the same thing from the original thing. But when you subtract the original signal, but its phase is slightly different from the original signal. Actually, 1 point delay, echo, okay? If you subtract this signal from this signal, then what you get is like this. Okay, there's nothing, 0, but we have an error. And when you subtract the echo delayed in 8 points, then it becomes misery. Like this. Subtraction result gives you more fluctuated component, more noise to your original signal because of the polarity of the sinusoidal signal. You can easily see that 6 pi over 50 and 6 pi over 50s. I cannot calculate. It's almost 2 pi delay when you delayed 8 point. Okay. Half pi. I mean. So this is what you see when you subtract something based on the sinusoidal signal domain, regardless of the phase. Okay, so you need to be very, very carefully decide the phase. But phase estimation is quite difficult, particularly when the signal composed from multiple sinusoidal signals. Okay. So I say subtracting noise is not easy. Simple signal subtraction is not easy due to the lack of the knowledge about the noise phase. Okay. So there are of course solutions in order to cope with this. One is the not estimating the one way to do is eliminate everything, okay, regardless of the noise and the real value, but just disregard the lower component. For instance, for the power supply noise case, 100 Hertz. So you lose the information of the signal in this frequency region, which is very low frequency region. But you get the very accurate estimate of the original phenomena in terms of the higher frequency of the behaviors, more than 100 Hertz. So, which is in other words called high-pass filtering. This is doable only when the noisy signal is concentrated in a very lower frequency component, and relevant information to your final goal are aligned in a higher frequency component, of course. But frequency filtering is one very common way to eliminate the noise. And second way is the spectral subtraction. This is very, very classical, but nevertheless, but still a very effective way to do that, to denoising. You can easily Google spectral subtraction. I cannot go in detail about what is spectral subtraction, but just show you one page slide. But if you are interested in and like to use this technology, you can Google. Okay, and spectral subtraction based on the spectral domain signal processing. So if you are not familiar with that idea, that are slightly difficult for you to understand, but spectral analysis is converting the time domain signal into the frequency domain signal. Those are called Fourier transform or Z transform or Laplace transform. All those transforms are the same meaning in terms of the spectral analysis. And you can calculate the power spectrum. Power spectrum is the amplitude component of the frequency signal, sinusoidal signal. Say, for instance, xk absolute is the because in general this component becomes complex signal, complex data value. Then this is either the amplitude of the complex value of the case spectral component of the original signal. And also you can calculate or you can mathematically derive the dk, which is a noisy signal spectral component at the kth frequency band. And then not subtracting dk from xk, but you just attenuate the amplitude of the observation signal regarding with the estimated power of the noisy signal, like this. So this is the power ratio between the observation and the estimated noise. And when you subtract from 1, this ratio, then it becomes proper amplitude that you have, that you need to put how do I say? But you need to put the or enlarge the observation. So, for instance, if this noisy component is quite small, then this value becomes closer to 1, and you can use the observation value itself for the estimation. But if this estimated noisy component is big, comparing to the xk, which is the observation, then this value becomes very small, and when you multiply this value to this, gives you a very small emphasis of this spectral component. Okay, I know you are not you don't like this mathematics and also. So but I bet this is quite useful technology, spectral subtraction. Therefore, please visit some sites and understand this idea, which is proposed almost 40 years ago, but still are used for your practical use. Okay, spectral subtraction. That is a word you must remember. Okay, and based on the spectral, in order to achieve the spectral subtraction, again, you need to know the spectral analysis of the time sequence signal. And that is another very important, study point. But I also afraid that I don't have enough time to go in detail. But let me show you one slide. Discrete. Oops, what is that? Wait. I skipped this slide. Sorry. Maybe I have to write down. But I don't have time. So, okay. Let me skip. Okay. Anyway. So this is the fundamental, representation of the spectral and time domain relation. Okay, and all discrete signal which has the length of n can be represented by this equation, which gives you a superposition of the sinusoidal signal weighted by AK. You see? And I don't know, do you agree or not? This is a reality. So you can go and forth from N domain, which is the time domain, and K domain, which is the frequency domain, because you see K here. When K is very high, then this very rapidly changing or rapidly alternating the sinusoidal wave. But if but anyway, this is a frequency component analysis, and in other words, inverse Fourier transform or Fourier transform. Okay, so when you convert time sequence signal into this form, and then you can disregard some sort of case, like for instance, if you like to pass only higher frequency component, then you can disregard the k equal 0, 1, 2, 3, 4, 5 to 10, for instance, if n is 256. Then you can disregard the lower component, which means that you don't need to be bothered from the power supply noise like 60 hertz in a 1000 frequency sampling rate. Okay, so this is another way, not like spectral subtraction, but frequency filtering is another idea. So for instance, in the previous, let me show you one example. Okay, suppose that SN, that is a target signal, which you really need to extract from the observation, is like this, given by this equation. The important thing is that this is starting from k equals to 1 to 4. Which means that this is a very smooth and low frequency component only signal, like this, very small signal. On the other hand, suppose that the noise is like this, okay, 6 pi over 50, which is less than k equal 4, for instance. 2 pi k. If k is equal to 4, then 8 pi, 6 pi. So this is a bit lower frequency component, like this. And when you add this and this, you will end up with this noisy signal, which is completely different shape from the original signal. And how can we eliminate this from this? Is based on the can be done based on the subtraction or spectral filtering. Alright. Oh, I'm sorry. I didn't include the result of the figure of the spectral filtering. So this is not a spectral filtering result. This is a result of simple subtraction. And when you accurately subtract the signal, then signal reconstruction becomes very fine. But if you don't accurately estimate the noise signal, then again the signal is very much distorted, like the original observation. But anyway, these are the very simple idea based on the subtraction, signal denoising. And unfortunately, this is not always the case that we do know the noise shape, or we do estimate the noise when noise is highly random. So the second part of this lecture will deals with random noise, which cannot be represented like this, sinusoidal signal or summation of sinusoidal signal. And this is more closer to the reality, random noise. So do you remember I don't know how many of you studied about the probability theory on a very fundamental level. I hope you remember a very fundamental notion. What is a random signal or random variable? You cannot observe the real value of the random variable, but you can specify the distribution, how much likely the particular value would be, that random would be. That is a distribution. Okay, so in the dice case, distribution of the dice value is even. The probability or likelihood that you see 1 is 1 over 6, 2, 1 over 6, 3, 1 over 6, blah, blah, blah. So you can know that how likely you get 1, okay, out of 6 values, or numbers, I mean. And the second very important idea or notion about the random variable is expected statistics, okay, expectation value. So what is the expectation value of the sum of three dices, Nakagaito-san? You can answer. What is the expected value of the sum of three dice throws? サイコロを3回投げて出た数の和の期待値を求めなさい。6分の7かけ3? Okay, so what is the expected value of the dice number? 2, 7? Then what is the sum of is that what you said? Okay. So then it's actually quite simply you can describe x1 plus x2 plus x3 because expectation of x is like this. Then you can calculate 3 times c x because x1, x2, x3 all have the same characteristics when the dice is fair. Okay, so x1 plus x2 plus x3, that is the target value that we like to calculate for the estimation and expectation, and it can be written like this because ex1, because this can be rewritten like this, ex1 plus ex2 plus ex3. And we all know that the dice is fair and it is stationary. Therefore, this is equal to this and this is equal to this, which end up with this. Then finally, we get an answer to 21/2. That is the expected value. So this is very simple idea, okay? But anyway, we have to know that the x1, this is actually random variable, and we can calculate the expectation value as an exact number. But we have no idea about what x1 is. Okay, all we know is distribution. But only with distribution we can calculate the expectation without knowing exact number of x1 and x2 and x3 are. So this is a probability theory. Great. So the random process is one level extension of the probability theory, which is extended based on the index n, like the data and signal. Random process xn is a set of random variables, okay, indexed by n. So the definition of the distribution function, as you know, is like this: probability that the value xn is smaller than small x can be calculated or can be described by one distribution function f sub of xn given by what denoted by x. Okay. So this is another very important relation between the probability and distribution function. We denote this idea with this. F is a distribution function of the probability, or random variable x sub n, which where the value of x sub n is less than small x. So the x value, x sub n, this is the random variable in x. But we still have n as an index for the sequence. Therefore, we do have a distribution function which has also an index n. That is a random process in its definition. And if the process is stationary, then we are very lucky. We can write that fx sub n, small x, is equal to x, n, which regardless of the this value, we can calculate. We can use this distribution function. Again, the distribution function is the only cue to know how this random variable behave. And with only knowing this distribution function, you can calculate the expectation value. So knowing the real value doesn't matter. Knowing the distribution function matters. And definition of the stationarity can also be built on the distribution function, which is independent from the index n. Okay, so so this is a brief brief look back of the random process. And again, I also like to introduce one, or review a very fundamental idea, but very important notion of the random process, which is the correlation function. So correlation function, usually you use this small n and m is in definition given by the product xn times xm, and its expectation. So again, this is time sequence. Suppose that this is 1 and this is 2, then this correlation function represents two, how two samples in a sequence mutually correlated. When this value is quite high, this value is quite high, then those values are quite highly correlated. Or if this value is very small, like 0, then all those data are, uncorrelated. In other words, independent from the previous sample, 1, 2. Okay, so this is another, how do I say, fundamental signal representation which is defined for the random signal. Okay, so again, remember in the introductory part, we saw that this kind of signal, and we can easily calculate the correlation between this and this, because this is the deterministic function. Therefore, we can calculate the number of the correlation between this and this. Two samples apart. Two samples apart from in K sample. But because this is not this kind of things, when you observe, random signal is quite interesting. When you observe first time, it looks like this. And when you observe the second time, it looks like this. And third observation gives you it looks like this. But all those signals has the same distribution function. And also, you can calculate the expectation value at the particular signal point, because this is random. Okay. So if you understand the random process, you can apply this idea to a lot of different applications. So signal and random noise. Okay, when the noise is random, then what it looks like? This looks like. For instance, this dotted line is the deterministic original signal. And when one random variable is superimposed on this signal, the signal should be seen like this. The global shape somehow preserving the original shape, but it's very shaggy, and also locally the order of the signal or correlation between nearby signals are distorted, completely destroyed. But mathematically, you can recover the information from this signal. Okay. So I will talk about two or maybe three or maybe two very, very easy and efficient way to eliminate this kind of random noise. The key issue or key idea is that the assumption that the average of the random noise is 0. Okay? It is never always, it cannot be always the case, actually. But assuming this gives you a very simple, way to eliminate noise. And actually, you can convert the signal so that the error component and its mean becomes 0. But anyway, suppose that the average or estimation value of noise component is equal to 0, then the estimated or expectation value of the observation signal becomes the sum of the expectation value of the real signal and also expectation value of the random signal. But expectation of the random signal is equal to 0, then you can find that the real value that you like to get from the observation. So this is simple math again. And again, because we don't know what is the actual extent, the random variable, how do we implement this idea in a signal processing domain is the issue. And that is not difficult, of course. Well, pretty easy. So let me give you one very rough idea. Again, the noise shape, because it is random, change every time when you measure. But the original signal that you like to get is never changing, okay? Then what you can do is do multiple observation one and again and again, doing the same thing, then you get the different versions of noise signal superimposed on the same signal. So you can superimpose those noisy signals, and if you are lucky, so that the average of the random noise is 0, then you can eventually, reach to the real value. You see this idea? Because, for instance, you look at this portion of the signal. In this signal, this noise is negative. Therefore, the observed value is bit, smaller than the real value. But the second time, third time, fourth time, fifth time observation, you get a big peak here, which means that the random noise at this moment is positive. And then this and this will be canceled, and you're going to reach to the real value. Because of the randomness of the noisy signal and zero mean properties, you can expect that the superposition of the noisy signal becomes better and better in quality when you superimpose. Okay. And another interesting idea is not doing the multiple observation, but do the single observation. But yet you see same signal, like here, 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 in a dot line. Because if you remember, how do we produce this dotted signal, which is a superposition of the sinusoidal signals, which has a fixed periodicity. Therefore, this is another periodical signal. Therefore, this and this and this are same signal. Therefore, if you do if you do extract this part and this part and this part and summing them up, then you're gonna get less noisy signal. So this is another version of the multiple observation of the noisy signal. Okay, or in other words, comb filtering. Okay. So those are the idea of the what we do, and this is the actual implementation of that process. It is simply calculate the local average, because this component reached to or converged into 0 due to the randomness of the signal. The local mean becomes the only value that you're going to get when you calculate the local value. This is quite similar idea of when you extract the trend from the periodical population growth graph, like you did. So local averaging becomes one very easy and feasible way to eliminate or reduce the noise. So local averaging is quite easy, right? You get a noisy signal like this. Sometimes it's very, very high comparing to the real value, and sometimes it's low. And you can calculate the average. Then probably you can get a value. You calculate the local average of these 5 points, 1, 2, 3, 4, 5 points, and estimate that local average as the real value of this time slice. Okay, then the average may be like here, okay? The effect of the very peaky component will somehow, cancel out with this small negative error, but you get still, high error for the high positive, displacement due to this peaky data, okay? So I have a new idea. I have a good idea for dealing with this. Not only applying the local averaging, but operating the median filter. So if you deal with the signal and you think that signal is noisy, I hardly recommend you to apply median filter. That is quite general and easy way to eliminate this sort of a peaky noise. Because simple averaging gives you this sort of displacement. But if you calculate the median filter is, what median filter does is like this. You get a 5-point and you apply median filtering for this 5-point. You're going to reorder the samples by the amplitude of the sample. In this case, 1, 2, 3, 4, 5. And third data, that is a median value of the sample. In this case, this. This is going to be the effective estimate of the average median. Of course, median and the average are completely different idea. But coping with this sort of very big change, median becomes better estimate with a real value than the simple average. So also, when you Google the median filtering, you got a bunch of examples and codes. So please remember the word median filtering and do apply if you have a headache with the noisy sequential data when you are studying. Okay. So here you can see several results of the artificial noisy data, noisy elimination. In this case, a median filter, and 5-point median filter, 9-point median filtering. Of course, if the length of the window for the filtering or calculating the local average gets longer, the more smoother shape will be obtained. Therefore, if you also like to preserve the fine structure of the original data, you try to how much, how do I say, cope or deal with the trade-off between relevance of the noise elimination and also preserving the preserving the dynamic component of the original signal. And this is the simple averaging smoothing. And how do you look the difference? Well, it doesn't, it doesn't change a lot, but, yeah. But, almost same result. But again, if the noise component is quite, unstable and exceptional, then median filter is better. By the way, calculating the median filter value is not easy because you need to resort the order of the data. Therefore, of course, simple averaging is computationally much more inexpensive. And computer is another way, or is another name of this sort of experimental, this sort of denoising method. And computering again gives you another better estimate. But because as you see, this component could not be eliminated by the computering, unfortunately, in this case. Unlike this result of the smoother. Okay. But anyway, here's a very easy way to implement the eliminating the noise. Of course, you have a lot of different versions of denoising method, but unfortunately, there's no general answer to the denoising question. You can try several methods and find your best way to your particular problem. But knowing these sort of things like averaging or smoothing or spectral subtraction would be quite beneficial for you, because those technologies are quite fundamental and applicable to a lot of applications. Okay, so this is the end of the first class, and next week, or I don't know what is the next time slot, I'm gonna give you some idea about regression and also the time sequence modeling in terms of the stochastic framework again. So if you have any questions, I'm happy to answer. Okay? Okay, then thank you very much. Enjoy your homeworks and labs. Okay, exercise.